The Mars helicopter Ingenuity was the first helicopter ever to not only fly around Mars, but also anywhere other than on Earth. At least it was the first human-created aircraft. I don't know about the whole alien thing, but let's not get into that. The Mars Ingenuity is a helicopter that has been flying around on Mars for a few years, and it is unique in a few ways. The first way is that it is the first extraterrestrial aircraft to fly around. The second is that it operates in a very low density atmosphere. Because Mars' atmosphere is very thin, it is about 0.02 kilograms per meter cubed, which is 1/60th of Earth's. Now, with an atmosphere that thin, it results in a unique condition where you have these very low Reynolds numbers and compressible flows at the same time around these helicopter blades. Usually, compressible flows occur at higher Reynolds numbers. So it is unclear how shockwaves form and their effects on the aircraft at such low densities. What's more, because this Mars helicopter was the first of its kind, its performance obviously won't be nearly as good as what we can make it, because we simply don't know how these low density shockwaves and general compressibility effects will affect the aerodynamics of the helicopter. As such, learning about these aspects will enable us to make far better helicopters for Mars and other planets too. For example, new aircraft will have better payloads or greater ranges or even higher speeds. Who knows, maybe even drag racing on Mars will be a thing in the future. Now, just to give you an idea about the conditions of Mars and the helicopter had to face on it, not only was the density of air of their atmosphere about 1/60th of Earth's, but the temperature was on average 223 Kelvin, so 50 degrees lower than freezing. And the speed of sound on Mars is only about 70% of that on Earth, because the atmosphere is mostly CO2 and is also much cooler. And also, if the atmosphere's pressure is only 720 pascals compared to Earth's 101,000, so less than 1% of Earth's. As a result of all of that, the helicopter's rotor blades were only operating at a Reynolds number between about 1,000 and 10,000, comparing to that of a regular helicopter on Earth, where the blades are operating at a Reynolds number of about 1 million or even greater, so 1,000 times greater than that on Mars. So some studies on such low Reynolds number compressible flows reported that the wake becomes elongated and is delayed more. What's more, the lift coefficient can decrease with increasing Mach number. So the study that reported that finding said that for their particular airfoil, the lift coefficient dropped because the compressibility effect delayed the transition to turbulence, and hence the laminar separation bubble that would form usually, it didn't form, and hence the lift coefficient dropped. Now, while other studies have shown some funky effects, they have been very limited to Mach numbers below 0.8. So the strange effects we are seeing here were found at relatively low Mach numbers and not even sonic speeds yet, which the helicopter on Mars is actually experiencing. So as a result, today we're looking at the effects of transonic speeds at these low Reynolds numbers on the Mars helicopter's blade profile. To do that, we're looking at a paper called Numerical Study on Low Reynolds Number Compressible Flows, let me zoom off, around Mars's helicopter rotor blade airfoil. So this is open access, so you can find it in the link below. Now, just a little more reason as to why the Reynolds number is so important here when it comes to airfoil's performance. So in figure 2, we see the effects of the Reynolds number on the maximum lift-to-drag ratio of an airfoil in general terms. We see that for the laminar boundary layer, so this region of the plot here, the maximum lift-to-drag ratio is far lower than when you have a turbulent boundary layer. And then when you transition from laminar to turbulence, there's this massive peak. It spikes up to a much higher value, and then you go to turbulence. So one major reason for that is that at higher Reynolds numbers, the flow over the airfoil has much more energy to stay attached. As such, you can push the airfoil to higher angles of attack and still have the flow attached, and hence you get more lift. And that also reduces the drag coefficient. You also get a smaller wake and lower pressure drag. So let's talk about this Mars helicopter's blade airfoil profile. And I think that is quite important because it is literally the first aircraft to fly around but powered on another planet. So the blade profiles are of interest. So we can see the profile in figure 3 if we go down here. The profile is designated a CLF 5605. Now, going from the blade root to the blade tip, the profile did change a little, but overall the blade profile was still very thin. It had a thickness to chord ratio of only about 5%, which is quite thin. That's getting to like Wright Brothers Flyer kind of territory and bird territory, which is very thin. And this maximum thickness occurred at 20% of the chord, which is pretty common. Now, it was a little cambered with a camber ratio of 4.9% occurring at 59% of the chord from the leading edge though. That is really far back. For a typical cambered airfoil, the maximum camber occurs at around 30% to 40% of the chord from the leading edge. For this airfoil, the maximum occurs well past halfway. So for the helicopter, the diameter of the blades was 1.2 meters, so a pretty decent size. So to find out the effects of transonic speeds at low Reynolds numbers on this airfoil profile, these researchers did CFD. They went through a bunch of Mach numbers to see how the shock waves formed and then affected the performance of the blades. So to begin with, they ran their CFD, at a Mach number of 0.6, which only corresponds to a Reynolds number of 15,400, and that is for like a person-sized helicopter. That's really low. Usually it should be like close to a million or so. And they said that they selected this Reynolds number because there is other CFD validation data to compare it to. So the reason why they have to settle for other CFD data to validate their CFD is because they say that these unique conditions on Mars, there is no wind tunnel on Earth that can replicate them. They also say that there is a wind tunnel that was designed to replicate Mars conditions. It's aptly named the Mars Wind Tunnel, but even then, it cannot replicate these specific conditions. So that's pretty amazing. So for their CFD code, they're using one called FA-star, which is FA-star, which is a compressible solver developed by JAXA, which is the Japanese Space Agency. And in table 3, if we come down here, we see some additional information about their CFD solver on the right here and their settings. So one thing that is interesting to me is that they use the gamma theta SST turbulence model down here. They say that they use this turbulence model effectively because it is capable of modeling laminar separation bubbles. Now, if you've listened to this podcast quite a few times, you know that I often talk about laminar separation bubbles, and you might be getting bored of hearing about them. If so, then I get it. Believe me, I get it. I spent several years investigating these things and how to model them in CFD. And when I got to the end of that period, I was so over them. It was a frustrating period because it was early in my aerodynamics career and I wasn't that knowledgeable about these bubbles. And they're also a little complex to understand and model. So it was kind of like nature's strength versus my weakness at the time. Anyway, this paper though, we see yet again them popping up. So that goes to show you just how widespread they are and hence how important they are to understand. So for those of you who don't know what a laminar separation bubble is, it is when you get a transitional Reynolds number occurring, and it is a way for the boundary layer to transition to turbulence. What happens is that the flow comes along the surface, and not necessarily an airfoil, but just the surface, but the adverse pressure gradient from the airfoil does help. And then as the flow goes over it, when the boundary layer is starting to get some disturbances in it, it then detaches from the surface. It then transitions to turbulence and then reattaches. In this separation zone, we get a recirculation region, which is the bubble. And actually, one thing I should mention is that I have noticed when doing these podcasts, if there is a term that I'm more experienced with, for example, laminar separation bubble, I say it even faster than normal. So for example, last week when I was talking about vortex generators, I wasn't pronouncing the term properly. And that's because I've said the term so many times that now I just try to say it as fast as possible so I can get on with the rest of the sentence. So I'm definitely trying to slow down when I'm saying these terms. But if you hear me saying something like a slack jaw, then you know why. So in this podcast, I'm going to be calling laminar separation bubbles LSBs. Anyway, back to the turbulence model they used, the gamma theta SST. So in my experience, it is a decent model for predicting LSBs, but it isn't the best model. The model that I have had the most success with is the K Omega SST one. So I'm quite interested to see how this turbulence model goes in the validation process. Again, it is just with other CFD, but it will still be quite interesting to see. So in figure 4, we see the domain of their 2D simulation. Let me zoom in a bit here. So we have an O grid for the domain, which is literally just a circular domain, and we don't really see that often. The airfoil is then placed smack dab in the middle. And they say that they used this type of grid because it doesn't really change the grid density when you change the angle of attack. That's really smart. So what this means is that pretty much regardless of the angle the flow is coming in at, the mesh the flow sees will be the same. There is no directionality to it. That means that the results will be more consistent. Now, I should mention that this is a very specific and advanced thing to think about, and most CFD simulations wouldn't really benefit that much from doing this, because the thing that most CFD simulations could benefit from the most is really just improving their mesh in general, their quality. The second thing that they would benefit most from, in my opinion, is the Terminus model, which also ties in very closely to the mesh as well. So they say that the Y plus is under 1 for all flow conditions, which is good. And by the way, if there are some CFD things that I'm saying that you want to learn more about, check out our courses for CFD in the links below. We go through these things in much more detail, as well as a lot of other things, like the different Navier-Stokes approaches, time stepping, and other solver settings. But with this CFD, the authors tested 3 different meshes to see how many cells they needed to use. Their courses mesh had 59,400 points, which I'm not sure if they mean cells or really just points, like nodes. If they're related, so it's not really a big deal here, but still, it's just a point. So the medium mesh fineness was 124,000 points, and the finest mesh was 163,000 points. And I would like to see that number for the finest mesh bumped up a little bit, because at the moment it is just a 30% increase, and that's probably not enough to really see the grid converging in results. Anyway, in figure 7, they show how these different meshes affected the lift and drag coefficients across the range of angles of attack that they're interested in. And I must say that I'm pretty impressed with what they did here, because for a lot of mesh independent studies, the researchers usually just select 1 or 2 angles of attack and base the decision on that. In this mesh independent study, they used 11 different angles of attack, and it is quite thorough here. So they went to a lot of effort to do this. For the drag coefficient in this right plot here, each mesh produces almost identical values across the range of angles of attack. For the lift coefficient, in the drag coefficient, there's just one little hiccup at about 5 degrees for the coarse mesh, but everything else is really nice. It's very consistent. For the lift coefficient, which is the left plot here, the coarse mesh produces quite different results across the angle of attack range. So the medium and fine meshes are much closer together. So the medium mesh looks good from this study to go with, whereas the coarse mesh is probably not as good. In terms of actually validating this model, in figure 5, we see the results from this CFD with the literature CFD results. Again, it's CFD, not experiments. For the drag coefficient, which is the plot on the right, the CFD here lines up very closely with the literature. For the lift coefficient, it isn't as close, particularly at lower angles of attack. So this CFD underpredicts the lift coefficient by about 50 counts in this, like between 0 degrees and 4 degrees. And this underprediction is consistent, which I find a little odd in this range. This means that there probably is a systematic error that's causing this 50 count difference. And I'm not sure what is causing that, but the researchers say that it is likely due to the different turbulence models they use between this study and the one from the literature. So the LSB and separation in general is apparently occurring earlier in this CFD than what's being shown in literature. So that's how the turbulence models can affect the results. And without experimental data, it is difficult to tell then which CFD is correct. The authors say that it is the fault of this particular gamma theta turbulence model, and I agree to some extent that this turbulence model isn't perfect, but it may not just be this CFD that is off. Perhaps the literature CFD is also off. From all of this, I would say that we can trust the general trends. As for the exact values, for example, a 2% difference, we probably can't trust. So overall, I'd say that this CFD is probably a 7 out of 10. It obviously lacks in validation, which they can't really help here. It lacks a little in the mesh independent study as well, which they could have done a bit better here, I think. But there are some strong points, such as the extent of the validation data, and they considered many different angles of attack here, which is very thorough of them. So with all that, let's move on to the results. Now, in figure 8, we see an incredibly weird LSB forming. This is for a Mach number of 0.6 and a Reynolds number of 15,400. So to begin with, at low angles of attack, the LSB looks pretty normal. It forms near the trailing edge. So back here, we can see the streamlines coming over, and then there's a separation zone here, and all these little white streamlines just like circulating around. That's the LSB. This effectively increases the camber back there and would likely increase the lift produced compared to if there wasn't an LSB. But as we get to high angles of attack, and especially at the highest one simulated, which is 9 degrees down here, the LSB is not only huge, but also extends well past the trailing edge. The trailing edge is here, and it's ending all the way back here. And then it bends back and reattaches to the trailing edge. It's really weird. I've never seen an LSB extend past the trailing edge like this, especially not like 30% past the chord. So the authors say that this is weird as well, and although not in so many words, I guess, they say that this is unusual for an LSB to occur, and it's probably an error due to the gamma theta SST turbulence model that is causing it. I would agree to some extent that this is probably an error, and probably the turbulence model is partly causing it. And could you imagine if there was like an LSB that looked like this? You have it extending past the airfoil, effectively increasing the chord of it and the surface area. Effectively, you have this bubble in the wake, and it could even produce lift. So I don't know how this is really possible to occur in real life. From these figures, I don't think we can really trust them past 4 degrees, because after that, the LSB starts to become really weird and strange, not really resembling real life, I think. So I'm going to downgrade what I said before about this CFD and rate it more at a 6 out of 10. Anyway, apart from that oddity, one trend that makes a lot of sense is that as the angle of attack increases, the LSB starts to form closer and closer to the leading edge. It marches forward. That definitely does happen and is very well documented in literature. Now let's move on to the effects of compressibility on this airfoil's performance. So in figure 12, if I scroll down here, we see the effects of going from a Mach number of 0.2, so that's the blue line, to a Mach number of 0.6, the red line, for the lift coefficient and the drag coefficient, and also the pressure drag coefficient, which is really cool. We rarely get to see the effects of different components on drag, like the pressure drag and the skin friction drag. Interestingly, when the Mach number increases from 0.6 to 0.2 to 0.6, the lift coefficient plot was greatly affected. First, at the long angle attack, the lift coefficient was much higher, but about 20% higher. And then secondly, at 4 degrees, the stall occurred for this higher Mach number, which is quite strange, given that at 0.2 Mach number, the lift coefficient was much more typical, where it just steadily increased with the angle of attack and didn't stall until past what they tested at. So this early stall at Mach 0.6 is likely due to the turbulence model that we mentioned earlier. So I'm not sure how accurate above 4 degrees is. Let's just focus on these lower angles of attack for this podcast. So from this plot, it is clear that the greater the Mach number is, that definitely increased the lift coefficient, and that's very beneficial. And the authors don't really go into why this occurs, but from figure 14, if we scroll down to these figures here, which show the pressure coefficient distribution over the airfoil, we see that at 3 degrees, the suction surface just has a low pressure coefficient over the entire thing, really. So the flow accelerates over the suction surface perhaps a little bit more, which then results in a lower pressure and then a greater lift being produced. In figure 12b, we see that with the increasing lift coefficient, the drag coefficient also increases at higher Mach numbers as well. This increase in the drag coefficient comes about pretty much completely because of an increased pressure drag, which indicates a larger wake, probably due to the LSB, I would say. With that, we can also conclude that the overall skin friction drag isn't really affected too much by the Mach number increase either, but that doesn't mean that the skin friction drag stayed constant with the Mach number. What I mean is that if the Mach number changes the LSB, which is logical, then the skin friction at certain regions will change because the near wall velocity is different. So what that means is that all these changes really just cancelled out, and at least that's what this plot is really indicating, because most of these changes are from the pressure drag and not from the alternate drag, which is the skin friction drag. So from what I can tell from this plot, about half of the drag coefficient is from the pressure drag and half from the skin friction drag. So in figure 16, we have a cool figure, which is a little trippy first once you look at it, and then once you understand it, it becomes a lot more comprehensive and comprehensible. So what this plot is showing is where the flow is separating over the airfoil at 2 different Mach numbers, Mach at 0.2, which is the blue line, and Mach 0.6, which is the red line. The y-axis is the angle of attack, so we see how the separation and reattachment points change with angle of attack. With that, we can then tell how big the LSB is. So the red line is for the Mach 0.6, as I mentioned, and we see that there is no reattachment point plotted on this graph. And I think that's just an omission of the graph, because we saw in figure 15, for example, that the LSB does reattach at the trailing edge and even at low angles of attack as well. And yes, at high angles of attack, it didn't make sense, but at low angles of attack, it does. So the general trend that we see is that for both Mach numbers, as the angle of attack increases, so we go up, the point at which this flow separates marches towards the leading edge, and that agrees with LSB literature 100%. Now, all of this is just fairly subsonic flow. What about transonic flow? Because we know that the Mars Ingenuity is flying around and the blades are experiencing transonic speeds. Let's move on to those results now, because this is what we've been looking forward to. So figure 17 down here, this is really cool. Let me zoom out a bit. Okay, so we see really cool shockwave patterns around the airfoil, and I actually recently covered the general shockwave pattern around a double wedge airfoil on YouTube, on our channel. If you're interested, it's called Supersonic Double Wedge Airfoil Aerodynamics Aero Fundamentals number 50. So one thing to note here is that we are seeing the density changes around the airfoil, which is not necessarily the shocks, but transonic and supersonic speeds, they are. So let's first cover the subsonic cases, this top row here at Mach 0.6, to get that out of the way. So these figures clearly show the LSB forming on the airfoil. In fact, I've never seen the LSB visualized like this in CFD, and I really like it. It's very effective and clear. Without all the other stuff you see, like the streamlines, this pertinent information just really pops. It's very easy and clear to see. Now at Mach 0.8, this second row here, we start to see what is called a lambda type shockwave forming. So these are different to normal shockwaves and oblique shockwaves and expansion fans. What is happening is these lambda shockwaves, as they come down here, it's like a lambda symbol, the Greek letter. As the flow accelerates over the airfoil, it hits the critical Mach number, then we get a shock forming. And then we will get a LSB forming here. And then once the LSB starts to curve back down, it then stretches the streamlines, and then that results in another shockwave forming, but now it's at a different angle. And that shockwave comes up and hits and intersects the original shockwave at some point, and it forms this lambda pattern. So that is what we see here. And as the angle of attack increases, the shockwave moves forward towards the leading edge. And this is logical because as the angle of attack increases, the point at which the flow accelerates to sonic is closer and closer to the leading edge. So we're hitting the critical Mach number sooner. Now at higher Mach numbers, for example, Mach 1, which is shown in the next figure here, we see not the lambda shock anymore. We actually get just a regular diamond pattern shockwave forming. And I think it's because we start getting an oblique shockwave at the start of the airfoil, which means that already the flow over the rest of the airfoil is already supersonic and no more shocks occur until the trailing edge. And that's where the flow on the upper surface meets the flow on the lower surface, and they change each other's paths, and that leads to further compression and hence shocks, which is why we get these two shockwaves at the trailing edge fanning out. Now at Mach 1.2, we get a shockwave standing off the leading edge, and that occurs because of extreme compression ahead of the airfoil. And we also get the rest of the familiar shocks over the rest of the airfoil, so this pattern at the back of the trailing edge. So what effect do these shocks and higher Mach numbers have on the airfoil's lift and drag coefficients? So in figure 19, we see a lift coefficient plot, and the lines are all placed over, like all over the place. It makes sense considering just how different the flow over the airfoil becomes at different Mach numbers and different angles of attack with lambda shocks, oblique shocks, and shocks at the trailing edge. And overall, the general trend is that the higher the Mach number is, the lower the lift coefficient becomes. In fact, at Mach 1.2 and Mach 1 and Mach 1.2 at 0 degrees, the lift coefficient is slightly below 0. So that is incredible considering that this is a cambered airfoil and it should be producing lift even at 0 degrees. It should be well above 0. So why isn't it here as sonic and supersonic Mach numbers not producing any lift? It's actually producing some sort of downforce. Well, the shocks that form ahead of the airfoil and even at the leading edge redirect the flow. So it is not coming really in at the same angle anymore. As such, the overall angle of the airfoil is now at low enough to produce negative lift. So what about the drag coefficient? In figure 9b, we see the quintessential sonic plot. As we approach sonic speeds, the drag coefficient increases more and more, as we see with this green line here, it's getting the highest. And then once you punch through sonic flow, and then it becomes supersonic, the drag coefficient then drops, as we see with the yellow line. It's slightly below the green line. The researchers say that the main component of drag here, especially as you approach sonic speeds, is the pressure drag. Now, I'm not really a big fan of what they just said. What they have done here is grouped the wave drag in with a pressure drag, which I guess you could do if you think about them as just pressure on the airfoil. But by grouping them together in this fashion, you make it harder to understand what is exactly happening, how to dissect the different components of drag. What is actually happening is that the shock waves I greatly increased the pressure upstream, which increases the drag, and that agrees with literature from the past 70 years. And with that, we come to the end of this podcast. I was actually quite surprised at how much the Mach number affected the lift coefficient at varied angles of attack. I also really liked their breakdown of the drag coefficient into the pressure drag coefficient too. That was a nice addition that we don't usually see. And it was really cool seeing the shockwave progression over the airfoil as the Mach number increased and as angle of attack increased as well, these figures here. And finally, if you want to learn how to use OpenFOAM, which is a very powerful CFD software, but very hard to learn, take our course. You can find the link below. We go through it step by step. We also have other CFD courses so you can learn how to do CFD better. And if you're doing experiments, which these researchers didn't do in this paper, but if you were doing them, then did you know that you probably have a 2 to 4% error in your results without even knowing it? So to correct for that error, we made the atmosphere hawk, which you can find in the link below, as well as the math showing why this 2 to 4% error occurs. So that is it for this podcast. See you next one. Peace out, amigos.